Okay, so looking at this example 8, it's asking us to compute the average rate of change. So that's the change in altitude over the change in horizontal. Um, Now, say we're looking at so we'll say average rate of change from A to B. So let's see, the change in altitude over the change in horizontal. Now the change in altitude, if we look at A tilde to B tilde, A is at an altitude of 2,000, I think is that kilometers? A unit of 2,000, and the B tilde is at a unit of 22. So the change in altitude is 200, I think that's meters. So the change in altitude from A to B, if we're looking at A tilde to B tilde, is 200 meters. And then the change in the horizontal, so they give us the scale that says that the distance, the horizontal distance from A to B is 200. So that's also 200 meters. So then that slope, it has a slope of 1, or the average rate of change is 1. Okay, but then if we look at the average, yeah, let's say, so the average rate of change from, say, A to C, okay, that's going to be the change in altitude by the change in the horizontal. So the change in altitude, now from A to C, again, we go from 2,000 meters to 2,200 meters. So that change is 200 meters. But then the horizontal is also given here, and it says that the horizontal change is 400 meters. So then this would be 400. So then we get an average rate of change of a half, or 0.5, from A to C. And then average rate of change from A to C, ABC to A to D. Okay. So that's going to be the change in altitude over the change in the horizontal. Now the change in altitude, as far as going up and down, now notice that D is on the same contour line as A. So we didn't change altitude, so the altitude would be 0. It has a 0 change. And then the change in the horizontal, I guess it doesn't really matter. It doesn't matter what distance, so we'll just leave it as the change in horizontal. Because, it's kind of like walking around the mountain on the same level. So then the average rate of change there would be 0, is what I would anticipate. Okay, yeah, so that's fine. Okay, so again, we notice that we see that the average rate of change varies with direction. So let's look at this. So when we walk up a mountain, the incline at each moment depends on the path we choose. If we walk around the mountain, our altitude doesn't change at all. On the other hand, at each point there is a steepness direction in which the altitude increases most rapidly. So on a contour map, the steepness direction is approximately the direction that takes us to the closest point on the next highest level curve. So figure 17a, we say approximately. So vectors pointing approximately in the direction of the steepest ascent. Okay. An approximate path of steepness ascent starting at P. Okay, that's fine. Let's keep it going. So we did 8. Let's go back here. Put this back. So because the terrain may vary between levels, a path of steepest ascent is a path that begins at a point P, and everywhere along the way, the points in the points in the steepest direction. So we can approximate the path of steepest ascent by drawing a sequence of segments that move as directly as possible from one level curve to the next. Okay, let's keep going. So more than 2 variables. There are many situations where a function of more than 2 variables is necessary. For instance, we might want to keep track of temperature at various points in a room using a function where the temperature is based on x, y, and z. So that depends on the 3 variables corresponding to the coordinates at each point. In making quantitative models of the economy, functions often depend on more than 100 variables. Unfortunately, it's not possible to draw the graph of a function of more than 2 variables. The graph of a function of x, y, z will consist of the set of points x, y, z, and then f of those inputs. That's a four-dimensional space in R4. So, however, just as we can use contour maps to visualize a 3-dimensional mountain using curves on the 2-dimensional plane, it is possible to draw the level surfaces of a function of 3 variables. So these are the surfaces with the equation f of x, y, z equal to c. So for example, say we look at the level surfaces of f of x, y, z equal to x squared plus y squared plus z squared. What did we say that was? Like an ellipsoid? These are the spheres. Okay, these are our spheres with the equation x plus y plus z squared equal to some constant. That's the c. So in the case of a function, as far as the temperature like we had, that represents the temperature of points in space, we call the level surfaces corresponding to the temperature equal to K the isotherms. These are the collection of points, all of which have the same temperature K. So that's a science notion. And this is getting interesting. For functions of 4 or more variables, we can no longer visualize the graph of the level surfaces. We must rely on intuition developed through the study of functions of 2 and 3 variables. Okay. So, beyond 3 variables, then, we really can't draw the images. Okay. So then this example 9, we're asked to describe the level surfaces of this function of 3 variables. Okay, let's see. The level surfaces, so if we set the output to 0, what kind of graphs would we get? Okay. Just for the sake of time, I'm going to use the solution that they have. Now, so, when we were... So we have a function in 3 variables, and we want to look at the level surfaces. So, before we had 2 variables, we were setting the function equal to a constant, and then what this was giving us was a snapshot, or it was giving us a 2D sense of what was going on with that 3D object. So now, since we have a function of 3 variables, when we set the function equal to a constant, it's going to give us, you got to step everything up one. So this is going to give us a 3D sense of what's happening with our 4D object. Okay. So, and now for me personally, when I try to visualize the 4D space, I like to think of it like I'm looking at some dynamic 3D object. So I'm looking at some 3D object as it moves through time. So this is where, like, okay, for instance, when I say the time is 0, it's going to give me a snapshot of what this 3D object looks like. And then say maybe after the time is a unit of 1, so when we increase time, what happens to the 3D object? So as we vary time, the 3D object is going to be kind of dynamic, and we're going to get a sense. So if we were using like a computer program, this is a quick recap. Like for instance, in the far left, we see that when C is positive, we'll get this kind of shape here. And then when the C is 0, it'll collapse to these 2 cone regions. So it went from like that hourglass shape that we have. What is that called? Does it have a... Yeah, the hyperboloid of one sheet when we have a C positive, and then when C goes to 0, it collapses to the point and then once the C goes negative, it goes into a hyperboloid of two sheets. So then you can put all of these 3D objects together, and we'll get the result on the far right. And so again, what's happening here, again, for me, just for my peace of mind, again, the thing that makes most sense for me thus far is that, since we have a function of 3 variables, and when we start setting this function to, when we're looking at the traces, it's going to give us, at each snapshot, it's going to give us a sense of what's happening in the 3D sense, giving us a hint to what's happening in the 4D sense. So like, for instance, when we set C to positive, we got a hyperboloid of one sheet, and then when the C was 0, it collapsed. You get the 2 cones, or the hyperboloid, where it comes to the tips. And then once it goes negative, then we get the hyperboloid of 2 sheets. And so again, when you think of it like time, it makes sense. When time was 0, then it's the center one where they touch, and then as time increases, you get a hyperboloid of 1 sheet, and it's dynamic and it moves. And then if you wanted to go back, in the sense of time, it's that's just conceptually one way that it can be visualized. Okay.